So what we were looking at yesterday, everybody, is how to calculate a magnetic force not on a moving charge. If you want to know the magnetic force on a moving charge, you use Fm equals QVB. That's what you do. Yesterday we learned that if you want to find the magnetic force on a wire carrying a collection of charge that's in motion, you use a different formula. And I want to point out to you that really they are, in fact, the same formula. When you have the magnetic force on a single charge equals QVB, that's for a single charge. Yesterday we learned the magnetic force on a current carrying conductor is ILB. Well, there are a lot of ways I can explain to you that these formulas are really the same. One of them is to say to myself that the V in this formula is distance over time, and I can wedge that time over underneath the charge and get that the magnetic force is charge over time times the distance traveled in the magnetic field times the magnetic field, but charge over time is current, and distance is length of the wire. They're the same formula, really. Anyway, this is the formula that you use to solve problems if you have an entire conductor carrying a current. Does anybody have any questions you would like me to go over? Ian?
How come in the formula the T can't go under the D and create velocity?
It can. That's maybe my point, is that if I put the T under the D, it's velocity. So I took an approach of showing you that QVB is the same as ILB. I could go over here and say I is charge over time, and then I could move the T under the L and say that's your velocity. So it just depends on which angle you're looking at it from. So questions? Yeah. Okay. So this has to do with the diagram or the graph and the setup. So all of the questions from 6 to 9 deal with this setup, which is actually on the next page. It says someplace there. So let's talk about what's happening here. In order to determine the strength of that horseshoe magnet, students set up the following experiment. What they have is some wooden supports just to hold the wire. And this is the current carrying wire. That thick piece of metal is what is in the magnetic field. Okay? And it's what is going to experience a magnetic force. If we take a look at the orientation of the potential difference, the positive terminal is here. And that means that conventional current, I'm a conventional current kind of guy, conventional current will be flowing in this direction. And that means that when the conventional current is in between the poles of the magnet, it is moving in. Okay? And the result here is that, I didn't indicate the poles here. Maybe I should next time. This is the north pole and this is the south pole of the magnet. So if we want to determine the direction of the magnetic force, I would hold my thumb in, my fingers north to south, and since I'm talking about conventional current, the force is downward. And they've set it up this way because this is going to tell them how many newtons of force that thing is being pushed down with. Are you guys with me on this? That the scale is a way to measure the magnetic force. And we should know, even without looking at a formula, everybody, you should know that these two things are related. Because if you increase the current, sorry for looking around this thing, if you increase the current, there will be a greater magnetic force. And the reason there will be a greater magnetic force is because the magnetic force equals ILB. Now this is a graphical analysis. They even give you the graph, right? There's the graph. You can even see there's the downward force and there's the current. So in this experiment, this is your dependent variable. I guess in science we should call it your responding variable. Whereas this is your manipulated variable. You've actually got a dial here where you can increase the voltage, and then this ammeter tells you what the current is. That's what an ammeter is. It's a device that measures current. So what they've done is they've set this up, and they've plotted the data for a variety of different currents. And they've created this graph. Now, what's interesting is when you look at this equation, this should have no y-intercept, right? And the reason is I've lied to you. This y is not the magnetic force. This is the magnetic force, but there's another force being measured by the scale. It's the force of gravity. And I didn't want to put numbers on here, but right now the current is 0, right? There's no current. Will there be a force registered? Well, yeah. It's going to be the force of the wire and the stands that the wire is on being pulled down because of gravity. So it isn't that I lied, I didn't think ahead enough. This is not our y. The force being measured is actually a magnetic force plus a force of gravity. This is our y, the force being measured, which is a sum of two forces. And if I start building an equation here, this force that's being plotted is equal to ILB. How many of you are okay with me just saying ILB could be written as LBI? How many of you know why I'm doing that? Why do you think it is, Annalie? Right. I'm trying to draw a connection here between y equals mx plus b. So since I've plotted current on the horizontal axis, I've plotted force on the vertical axis, I've plotted current on the horizontal axis. What that tells me is that LB is my slope. So just think about that for a second. Forget about what questions may or may not be asked. If you were asked to determine the magnetic field strength, which is what these students are trying to determine, in order to determine the strength of the magnetic field, what you would do is you would find the slope of the line and divide by the length of the wire in the magnetic field, because the slope of the line equals the length of the wire times the magnetic field. If you were asked what is the mass of the wire and the support stands, you would find the y-intercept and divide it by g to get the mass. Let me highlight the final thing here for a comparison, and then we can get to the questions. I hope it's obvious, but just in case, the M here that I've highlighted as part of the pink is different than the M that I've highlighted in yellow. The M in yellow is the slope of the line. The M in pink is the mass. So if you're asked, well, what's the strength of the magnetic field? We've determined that the slope equals the length of the wire times the magnetic field. So to get B, you take the slope divided by the length of the wire. Okay? We'll get to the calculations in a second. What is the mass of the wire and supports? Well, we've determined, based on this comparison with all the highlights, we've determined that the mass is related to the y-intercept. And specifically, the y-intercept is equal to m times g. So if we knew the y-intercept, we could just divide that by g to get the mass. For 8 and 9, once you have the slope and the y-intercept, you're going to use that equation to find the missing data. So for example, in number 8, you've got 11.3 amps, you're going to put that in for X and calculate what Y is. You're not going to use F equals ILB. You have to use the equation of that line. And then for number 9, you've got 19.5 newtons, pardon me, 1.95 newtons. For question 9, you're going to put that in here to get X. So I don't mean to minimize the rest of the work we have to do, but everything I've explained is the physics, right? We have some math to do now. One of the things we need to do is find the equation of that line of best fit so that we will know the slope and the y-intercept. And I'm thinking the quickest, most efficient way to do that, I know you can read the y-intercept, but I think the most efficient way to do this is to do a linear regression using 2 points that we can read very accurately on the line. So I don't know if I can find 2 that are nice and precise. I'm going to go with that one. It's not quite exactly on the crosshairs of a grid, but it's close enough. And I'm going to go with this one. You know, you feel free to read that data however you feel it can best be read. So you go Stat Edit. If you have anything in there, you can go to your Memory Management menu, second plus, and choose Clear All Lists. That will do it. Or you could reset your calculator memory, which I think is not necessary. The first data point, this is 0 to 1, so each of these squares is 0.1, and I can see this is at 0.6. I just want to make sure I read it correctly. It's 0.6 amps. It's not 0.6 times 10 to the 2 or anything. So I can put in for X 0.6, and for Y on the other side, for L2, let's see, 5 squares is 1, so each of these is 0.2, 0.2, 0.4, 0.6, 0.81. This, however, is times 10 to the negative 1. So when I read this Y coordinate here, and I say it's 4.4, it's 4.4 times 10 to the negative 1. Or 0.44. For my X for this point, it's 3.2. And my Y is 6.6 times 10 to the negative 1, which is 0.66. Just double check that before I commit to doing the regression. 0.6 and 3.2. And then vertically we have 4.4 times 10 to the negative 1 and 6.6. I think it looks fine. So now I'm ready to do the regression. I go to my Stat menu again. I go to Calculate. I choose Linear Regression. And your calculator, you're going to have to hit Enter a few times to get through all of those menus. I get this. So if I go back now to here, I know that the slope is 0.084615. I know the y-intercept is 0.389. What I'm going to suggest to everybody is I've explained what to do at the beginning of tomorrow's class. If you like, we can come back and do the calculations. But again, if you are after the magnetic field strength, which, by the way, magnetic field is capital B. I hope you understand that capital B is different than the B on my calculator screen. Right? That slope of 0.0846, we can set that equal to LB. Somewhere in the question, it's going to tell you the length of the wire in the magnetic field. You would divide by that to get B. For finding the mass, you would take the y-intercept, 0.389, and you would divide by g. Somewhere in your mind, you know what g is, 9.81. And then again, to answer 8, you have to use this equation, not the physics equation, not the ILB, but this mathematical equation, and you put in 11.3 for x, multiply your slope times x plus b. Are you okay to finish it from there? Okay. Any other questions before we get started today? All right. I have a quick demo to show you. Yesterday I showed you a demonstration of the motor effect on a current carrying wire using this. Remember that? Yes? This was just to demonstrate that the right-hand rule works. Well, we're going to do the same thing here with this little thing that I put together. And, you know, later on we might have some time at the end of the class. You can come and take a look at it closer. It's a portable thing, though, so I can move it around and show different groups of people. What I have is, let me show it to you visually here first, is I have a broken iPod. I have two magnets. This is a south pole and this is a north pole. So the magnetic field in this region in between them is north to south. So I guess if I hold it this way, that's what it looks like. And what I also have in there are some neodymium magnets, very, very strong magnets that are oriented the same way to create a very strong magnetic field. And then I have a piece of aluminum foil running through the middle. And it's connected, the aluminum foil, one end is connected to an alligator clip, which is connected to some housing electrical wire, which is very rigid. Like you bend it and it stays in that shape. And then it comes up over here. And the other end of the aluminum foil is connected to another alligator clip, which is connected electrically to here. And I can adjust the tension of these clips and move the foil up or down. But the bottom line is if I connect a potential difference to these two wires, there'll be a current that goes through the foil. Now, foil has a very low electrical resistance, so I don't want to leave it connected too long because it'll just melt. Okay. I'm going to use 3 volts of potential difference in the form of a battery or a set of batteries to do this. So let's take a look at the orientation I have here on the screen. If I were to connect a negative, what color should I use? A negative here and a positive here, what direction should that foil be forced due to the flow of charge in it? So this is no different than the swinging arm. It's just a different, well, it is different. The principle is the same, right? I would point the fingers of my right hand north to south. So I imagine my hand inside of here, right? I'm going north to south inside. And my thumb, which way will my thumb point? Well, if you're a conventional current thinker, your thumb is going to be coming out towards the negative terminal. So if I were to connect the negative on the front of this and the positive on the back, the aluminum foil should be forced up out of the palm of your hand. And I'll just do that here. What am I doing? That didn't sound very good. Positive, negative. So the negative is the black, and I'm going to connect the negative to the front. And now I'm just going to pop the positive on and connect the positive here. And we're keeping an eye on the foil. And it moved up. You can even hear it. Right? And foil's kind of rigid, so if I connect this and it moves up, it falls a bit due to gravity. It will still move up a little bit every time I connect it, and the tension is bringing it back down. I'll just move it over so some other people can see it. Go over here. I'll move it down so you can see it clearly moves up. We'll go over here as well. Can you hold that? If I switch it now, thank you. If I switch it and put the negative at the back and the positive at the front, I mean, I think many of us know we don't have to use the right-hand rule again. We can just say if I switch the direction of the current, the force will switch. This should now be forced down. Once again, Jack, please. It should be forced down, and it is. Okay? And then the tension kind of pops it up again. And can you feel the foil? It's nothing connected. You're fine. It's a little warm, eh? Mm-hmm. That's from the high current in there. So can you hold that? Thank you. So it goes down. And if we were to, I'll just show on this side as well, although I think you get the idea. It's a nice visual, though. It's kind of a nice, I think you guys can see it from there. It's kind of a nice visual, something that you can remember as an example of the motor effect. If I were to connect this, and we don't have time today, but I might set it up for you later. If I were to connect it to an alternating current potential difference, which is what we typically have in all of our electrical outlets, not typically, which is what we have in all of our electrical outlets, it will vibrate up and down. And that's an electric buzzer. Okay. Just another example of the motor effect. So today what we're going to be doing is completing example 6 from the previous day. So I need you to go back to page 64. And then we're going to be slowly working our way through an understanding of Lenz's law, which is going to carry into tomorrow. And even if I started the lesson with no questions and I didn't show you that demo, we would still take today and tomorrow for Lenz's law. It's a very slippery thing to try to grasp. At the top of page 64, we have 2 wires that are carrying currents in the same direction. And I can't get this battery charged enough to show it to you. I will try to get a different battery for tomorrow or next week to show you this in action. But if we have 2 wires that are carrying a current, there will be a magnetic force between the wires. Now keep something in mind. The wires are made of copper. There's nothing magnetic in terms of a magnetic metal that are composing the structure of this stuff. It's just copper with insulation around it. But we know, and this is tricky as well, we know that that top wire that's carrying a current has a circular magnetic field around it. Are you with me? Okay. So we know the bottom wire is in a magnetic field. It's in the magnetic field of the top wire. And we know, based on that little demonstration I just showed you here, and the hanging U-shaped swing demonstration that I showed you yesterday, that when you have a conductor carrying a current in a magnetic field, it's forced. And what that means is, this is tricky. Let's call this wire 1 and wire, I better not use that. Let's call it wire 1 and wire 2. I don't want to use capital I because that could be confused for current. What that means is that wire 2 is a current-carrying wire in the magnetic field of wire 1. So wire 2 will experience a magnetic force. But wire 1 is a current-carrying wire in the magnetic field of wire 2. So wire 1 will experience a magnetic force. And we can predict the direction of the magnetic force on either of these wires by using the flat right-hand rule. And it's one of the reasons why I started with this demo this morning. This demo in principle that we just did is no different than this, except this is like the foil, and this is the permanent magnets in the demo when we want to determine the direction of the force on wire 1. When we want to determine the direction of the magnetic force on wire 2, this is being like the foil, and this is like the permanent magnets. So the first thing we have to do is figure out which direction the currents are flowing in these wires. That's pretty easy. The currents, I'm using conventional current, are both to the left. So in wire 1, you have current this way. And in wire 2, you also have current this way. Now comes the tough question. And I'm going to just throw it out there and see how many of you can come up with an answer on your own. What is the direction of the magnetic field created by wire 2 that wire 1 is in? Let me just paraphrase that. Wire 2 has a magnetic field created around it. Curly right-hand rule. That magnetic field extends through space around wire 2, which means it's going to interact with wire 1. I'm asking, what is the direction of the magnetic field of wire 2 where wire 1 is? This is almost identical to a question on the quiz. How many of you feel you know? Ian? Into the page. Because, and I don't know that you need to draw this, and I worry that if you draw it, you might confuse yourself. But there is a circular magnetic field around this wire 2 that looks like this, right? Are you with me? Except the size that we draw this as is totally arbitrary. There's magnetic field lines everywhere. So if I increase the size of this, at this point in space, the magnetic field is coming up and going in. So this is the magnetic field around wire 2. If you want to draw it, you could label it as B2. And at this point, the magnetic field is in. So now we have a current-carrying wire carrying current to the left with a magnetic field in. I point the fingers of my right hand in, my thumb to the left. I look at the palm of my hand, and it's down towards the bottom of the page. If you're doing this on paper, you're sitting at your desk holding your hand like this. So there is a magnetic force on wire 1 towards wire 2. Now, what if I did the same thing and I say, what is the direction? And this is going to get really ugly. And I say, what now is the direction of the magnetic field from wire 1 where wire 2 is? Well, we're going to have the same circular magnetic field, aren't we? It's still going to look, and I've blurred this out because I don't want to be distracted by it. We're still going to have, based on the curly right-hand rule, that magnetic field around number 1. So what is the direction of the magnetic field from wire 1 where wire 2 is? Well, it's out. The magnetic field around wire 1 is coming over the top, down behind, and coming out below, and that's where wire 2 is. So what we have now is a magnetic field, and I said this would get messy, B1, that is out of the plane of the paper, and wire 2 is in that field. So let's see, fingers out, conventional current to the left, up. The magnetic force is up, which tells us that these two wires will be pulled together. And that's what I would do if I had my car battery charged enough, is I would create, this would be the situation here, I would connect this top to a negative, the bottom to a positive, and as soon as I did that, the wires would come together. There's a lot of friction between the wires and the board. The wires are stiff. Even my high current power supply won't do anything. I need a car battery that I'm essentially going to short out and have zero resistance and just have like maybe 40, 50, 60, 100 amps of current momentarily before it all melts. Okay? So I will try to charge the car battery. You can go through the same procedure. If you switched one of the currents, you would discover the forces are in opposite directions. Okay. All right, we're going to move on and start with what's called electromagnetic induction and Lenz's law. And I would say that this whole lesson is maybe maybe the most difficult set of ideas in Physics 30. More difficult, I think, than two-dimensional collisions. But if you break it down, it's not bad. It's just that there's a lot to it. We're going to be talking here about something today called the generator effect, which is not the same as the motor effect. That swinging arm, that U-shaped swing, that aluminum foil that gets forced, those are examples of the motor effect because I use electricity to create motion. And that's how an electric motor works. A generator is something that uses motion to create electricity. So it's the opposite kind of thing that's going on. And once we understand the generator effect, we'll be able to explain something called Lenz's law. And I've never done it this way before, but I'm going to start off with a demonstration of Lenz's law. And this is the classic kind of demonstration. You have a roll of aluminum foil, and you also have a magnet. And the thing to remember about a magnet, a magnet is magnetic, right? I'm not lying to you. That's really a magnet. The thing to remember about the aluminum, though, is aluminum is not magnetic. Like this magnet is not attracted in any way at all to this roll of aluminum foil. So what you're going to observe here has nothing to do with an attractive force between the magnet and the aluminum. Now, if I were to measure the length of this aluminum tube, it is 30 centimeters long. And a basic Physics 20 question would be, if I dropped an object, how long does it take to fall 30 centimeters? That's a very short period of time, isn't it? We could actually do the calculation here. It's a d equals a half at squared situation. 30 centimeters is 0.3 meters equals 1/2 times the acceleration, which is 9.81 meters per second squared. There's no need to use negative 9.81. We know it's moving down. Times t squared. So do me a favor, run that through your calculator and figure out what that time is. So you go 2 multiplied by the distance and divided by 9.81 and take the square root. Is that looking right? Okay. It's just so small. It seems like maybe I did something wrong, but it's a tiny distance. Take the square root of the answer. Man, you're looking at about 1/4 of a second, okay, for something to fall the distance of that tube. So Annalie, can you hold your hand out underneath? You'll catch it. I don't know how long that was. It had to be 2 or 3 seconds. We'll try it again. 1, 1,000, 2, 1,000, 3, 1,000. I was counting a little fast, so somewhere between 2 and 3 seconds. It falls incredibly slow. We can do that with other situations. This is aluminum as well. I could use copper, but copper pipe is very expensive. Aluminum's cheaper. So, you know, this might be $80, literally $80 for this aluminum. The copper might be $200 or $300. Okay. Now you're going to probably hear this magnet. It's a little bit smaller. You're going to probably hear it scraping along the sides, but it fits in pretty well, right? It's not like it's going to be scraping along the sides, and that's why it falls so slow. That's a long time. If we want to, you know, go nuts, could do this with, thank you. With this monster, will it fit? Yeah. And this is there's a good YouTube video of some of these demonstrations where I do it, I film it with a tiny magnet, and I say, if we were in class, this was during COVID shutdown, I say if we were in class, I would use this instead, and I'm holding this magnet here and this magnet here, and guess what happens? they come together, and I hurt myself. I get a boo-boo. Again, you can hear it, but it's just a minor scraping. It's not moving so slow because of friction. And this is Lenz's law. Something's going on, and these things are incredibly strong magnets, but this is not magnetic. The key to Lenz's law, and we have a long way to go before we can explain this, is that this is a conductor. So something is happening to produce a magnetic force on that magnet, which slows the thing down. And it doesn't have to be a magnet inside of a tube. So I'm doing things backwards today. I'm showing you Lenz's law first. What I have here are ring magnets, and they're in some kind of plastic here, just so that if they happen to come together, they don't break. And this is, I guess, the equivalent of dropping the magnet through the aluminum, but we're doing it from the outside. And I have three materials. This is plastic, PVC plastic, I think. This is copper, and this is aluminum. So if I drop this magnet, I mean, it falls as you would expect it to fall. But if I drop it around the aluminum, I guess it's a visual that you can see it moving slower. One of the questions we're going to be asked sooner or later is this: which is a better conductor? And the answer is the copper is a better conductor, because whatever is going on is connecting electricity and magnetism, and the effect is greater with copper. Copper is a greater conductor, a better conductor. That's why it's more expensive generally. That may be a lie. It may be just more expensive because it's rarer, more expensive to refine. I mean, I can show you other situations as well where I have a pendulum here, and the pendulum has magnets on each side of it. And what I have are aluminum blocks, and these aluminum blocks are quite heavy. They're probably about 2 pounds each. So if I put the aluminum blocks on both sides of the magnets and I drop the pendulum, it pretty much comes to a stop. I'm going to turn this over so I don't have them sliding around. It pretty much comes to a stop. This is what's referred to as magnetic braking. And it slows the object down very quickly, and the reason why it's a very good form of braking is there's no friction. If you know anything about automotives and brakes, you have to replace brakes because there's physical wear and tear due to the friction. You have to replace the rotors and the discs and the drums and all that other stuff and the pads. But magnetic braking doesn't have any friction. So how magnetic braking works for a train is a train has an electromagnet on both sides of the undercarriage of the train. And when that train enters a station where it's going to brake, some of the tracks are made of aluminum, a very good conductor. They flip on the switch to create an electromagnet that's operative, and Lenz's law takes place. So I guess I can tell you to begin with here, Lenz's law is basically saying when you have a magnet and a conductor moving past each other, there's a force that will always oppose the motion. I mean, there's a whole bunch of stuff in between those two events that we have to explain. And I hope it's obvious. It might not be. That it opposes the motion. So if I drop this from this side, it stops. If I drop it from this side, it stops. The direction doesn't matter, right? And if you actually get a chance, I don't have the track, I'll get the track out tomorrow maybe, and you just take one of these magnets and put it in your hand and you try to move it past or across a sheet of aluminum, it feels like you're trying to move it through syrup. There's this mysterious kind of force that's trying to slow you down, and you change direction and it's still there. So that's what Lenz's law is. We're going to start off with the very basics. So this has to do with electromagnetic induction, and if you like, you can put at the top where it says electromagnetic induction, generator effect. What we are talking about doing here is generating electricity. And again, this class ends at 10:40. Okay. I will try to time things right so that we don't end kind of in the middle of an idea. Consider having a solid piece of copper, that's that brown thing that I've drawn here, and I'm moving it through a magnetic field at a speed. The speed is the velocity vector given as v, and it's in red. So I'm moving that conductor. Okay? It's not a hollow pipe, it's a solid piece of metal. Okay? The first question says, how is it that when I'm moving the rod through the field, I'm moving electrons through the field? And it's kind of a weird question. I'm pulling the rod through the field. Why is it that that is the same as pulling electrons through the field? Can anybody answer that? And the answer is kind of unsatisfying because maybe it's too obvious and you might not think of it. Well, that's it. There's electrons in the rod, right? They go along for the ride. I can't just move the rod and leave the electrons behind. So what's going on here is the rod contains many electrons. So when you move the rod, you move electrons. But what that means is you have electrons moving in a magnetic field. And here's where the difference lies between today's stuff and what we've talked about before. We're in this demonstration with the aluminum foil, were electrons moving through a magnetic field? Yes, because they were moving in the foil, and the foil's in the magnetic field. The difference is with that, they were moving because we had an electrical source. In the motor effect, you have to put electrical energy in. These electrons are moving in the magnetic field because we're physically moving them. We're putting in mechanical energy, not electrical energy. What happens to charges whenever they're moving in a magnetic field? Well, let's just take a look at this in terms of kind of the motor effect. When you have a charge moving in a magnetic field, the charge experiences a force. And again, this is very subtly difficult. When you look at this demonstration with, and I'm just going to unconnect the battery. We know that there's really a battery connected to this. When you look at the demonstration we started off with, the electrons in the wire experienced a force because they were moving in a magnetic field. But they were moving in a magnetic field because I had a battery pushing them through the magnetic field. The electrons in this rod are going to experience a force because they're moving in a magnetic field, but they're not moving because of a potential difference. They're moving because I moved them. And that may seem like a very unimportant distinction, but it's really important. If electricity is moving the electrons, that's a motor. If you are moving the electrons, that's a generator. Okay, so the charges in this case experience a magnetic force. So there are the electrons. When I pull the rod, I'm pulling those electrons. Okay? It's that simple. Next question says, use a hand rule to predict the direction that each electron will be forced due to me moving the electrons in that direction. So we're still using this right-hand rule. It's just that now your thumb is not current. Your thumb is the direction you're physically moving the wire. And the magnetic field is, well, let's see. The magnetic field is in, X means in. Our thumb is to the right. If you're doing this on paper, I fear sometimes that you do it all the time up here and then you get to paper and you don't know what to do. If you're doing this on paper, you have to hold your hand like this, almost to your side. Otherwise, or you have to stand up, right? But this is the situation you find yourself in, which means that if you're looking up here, the back of your hand, because we're talking about electrons, are forced towards, or is facing the floor. If you're looking on paper, the back of your hand is forced towards the bottom of the page. So what happens is the magnetic force on each electron is towards the bottom of the page. Or towards the bottom of the rod. And then it says, so what does that create? What happens? What have we actually created now by moving the rod? I know that's a very open-ended, almost vague question, but I want to pick your brains and see if you can come up with an idea. Jack?
Electricity.
In a very general sense, we have created electricity, and I'm actually really glad you said that. That's not the answer I was looking for, but I want to highlight again at the top, I told you this is called the generator effect. And what we've done is we've moved something to create electricity. I'm going to get more specific in a second. It's like, you know, on the Flintstones, you're familiar with that old show, The Flintstones? There's one episode, I think, where Barney takes apart his microwave oven because it's not working. It's not an actual episode, but let's imagine it is. And inside, he discovers there's this little tiny dinosaur that runs on a treadmill and creates the electricity. But the dinosaur's hungry and is weak, so he's not doing any work. That's a generator. When you crank something or you physically move something to create electricity, that's a generator. That's how all of our electricity is created. All of it, whether it's created from natural gas, whether it's created from burning coal, whether it's created from a water dam called hydroelectric, whether it's created from, there's one exception, whether it's created from nuclear, the exception, whether it's created from wind, all of those things take energy in our universe and cause them to turn something to create electricity. The exception is solar. You go light directly to energy, and we'll talk about that in Unit 3. So now, I mean, I can show this to you. If I take these bulbs and I've got these bulbs wired. I'll talk about how they're wired in just a second. And I have a little handheld generator. And I connect them. I can create electricity. These are wired in such a way that if I, would you mind cranking that? Relatively fast. We want to get them nice and bright. Go. Come on. They're wired in such a way, keep going, that they don't have to all be on, right? This is how things are wired in your house. Thank you. The alternative to wiring this way, and this is called, how many of you know it's called parallel? Might have heard that before. It might be something from elementary or junior high science. As opposed to in series, so here I've got the wire going through all of the bulbs and coming out. There I had the wire connected to each bulb. If I do this type of situation, go ahead. I'll just hold it. Okay. Keep going. Nothing. Do you notice, by the way, it's very easy to turn? Turn it. Harder to turn, isn't it? Lenz's law. That's Lenz's law. That's exactly what's going on here. It's a little more complicated to explain. This is why houses are wired. I'm getting a little off topic, but I think it's important. This is why houses are wired this way. If I get up in the morning and I want to make some toast for breakfast, I can turn on the toaster. I don't have to run the toaster, turn on every electrical device and turn on every switch in my house so that the toaster can get electricity. How many of you have experience with Christmas tree strings of bulbs where if one bulb goes out, the whole thing is shot? They're wired this way, and that's why they're so cheap. This is very easy to manufacture. This is more work, and it's more expensive. Anyway, that's the generator effect. Now let's get back to what Jack said. What does this collective force on all of the electrons result in? Well, it results in electricity. Can you be more specific?
Electric current.
And the answer is going to be no. I'm glad you said that, though. There is a shift of the charge, but there will not be a flow of charge. There will be no electric current. Can somebody explain why, when those electrons shift to the bottom of the page, you won't get a flow of charge? I'll just show you the picture first. Boom, you move it, they all crunch down there. Why is there no flow of charge, Annalie? There's nowhere for them to go. And again, when Ashley was cranking that thing, if there wasn't a complete circuit, there was no current. It was very easy to crank. As soon as I connected it, then you got the current, then you got the resistive force, which is not directly related to this, but it's close. So it's not current. What do we create instead? Will? It's actually not a magnet, no. It doesn't have a north and a south pole. What we create is a voltage. But there's no current because it's not connected to anything. What we create, and this should make sense now by looking at the diagram, is the top of this becomes positive, the bottom becomes negative. So what we have is a potential difference. We have something that is ready to create a current if we connect it to something. When you crank that generator, if it's not connected to anything, all you're doing is shifting the electrons from one terminal to the other. And obviously that generator is more complicated than a single rod being moved through a magnetic field. We'll talk about that later. So the magnetic force on each electron is towards the bottom of the page. What does this result in? Well, the top of the rod becomes positive and the bottom becomes negative. More importantly, there's a potential difference. And that we still have, there's a whole chain of events that leads to Lenz's law and explaining why that magnet falls so slowly in the aluminum tube. But this is the start. This is what goes on in an electrical generator. That process of generation of electricity is sometimes called electromagnetic induction. And I hope intuitively it makes sense that if you crank that faster, you will get more current coming out when you connect it to something. You get a greater potential difference. I hope it would make sense that the strength of the magnet is going to affect the voltage you create. Right? So inside of this little handheld cranky thing, which is called a Genicon, it's a little generator, there's this metal casing, and inside of that are pieces of wire that are all coiled together, and there's a magnet, or a series of magnets. If I move it faster, I get more voltage, and if I used a stronger magnet inside, I would get more voltage. The other way I can get more voltage is to have more wire that's in the magnetic field. We talked about this the other day, that rather than just having a single piece of wire going across the magnetic field lines, we could have the wire wrapped in a coil. Essentially what we can have is this. And there's a magnet around here, and you're spinning this. And all of these wires are moving through a magnetic field, generating a flow of charge, which creates a potential difference between here. But again, you don't get a current unless you close the circuit. I'm going to show you a formula here. It turns out that the potential difference can be found by multiplying those three things. If you multiply the magnetic field by the length of the wire in the magnetic field, by the speed, you get the voltage. This is not on your formula sheet. This is not something you need to memorize, but it is something that I very frequently see on a diploma exam that will give you that formula as part of a question. It's also something that I want to refer to a little bit later. So now I want to show you some other demonstrations which are probably more boring than the Lenz's law ones, but nevertheless I think they're important. And all I'm going to do here is demonstrate to you the generator effect in a very clinical way. I have what's called the galvanometer, and a galvanometer is basically an ammeter. It measures current, but it's very sensitive. There's a little bit more to it than that. And this galvanometer, I don't know if you can see, the needle is at the top here. You guys have good eyes. Can you see the needle is at the top? And the reason it's at the top is this is capable of measuring a flow of charge in one direction and a flow of charge in the other direction. And if I were to just put this coil of wire, which is connected to the galvanometer, next to a magnet, there's no current. Okay? I tried to find some longer leads, and I apologize. There's no current. There's only current when I start to move the magnet in the vicinity of the coil. As soon as it stops, I get no current. The perfect or ideal way to get a current is to move the magnet through the center of the coil. So I have a bar magnet. I move the south pole in, and it generates a current to the left. Sorry, to your right. I move the south pole out, and the current is generated in the opposite direction. When I move the south pole in, the current is generated to the right on this scale. Then when I move the north pole in, it would make sense it would be generated to the left. I mean, we can't drill down and use the right-hand rule with these little tiny wires. You can't see them, okay? But if I move the north pole in, it moves in the opposite direction, okay? If I move the magnet slow, I get very little current, right? Whether I'm moving it in or out, if I move the magnet slow, I don't get a lot of current. But if I move the magnet quick, I get more current. Yes? If I go to a stronger magnet, and you'll just have to take my word for it that this is a stronger magnet. If I use a stronger magnet and I move it in, will it fit? Yeah. And I move it in slow, I mean, I'm hardly moving it at all, and I'm generating a lot of current. Okay. If I use more coils, this has, and my eyes are no good, someplace on there, I don't know which way it is, it will give you a number and it will say WDGS or something. 400 windings. Can you read what that one says? Thank you. 1600. So 4 times as many loops of wire. By the way, this wire is nice and shiny, isn't it? It does have insulation on it. So lacquer insulation. So the strands of wire are not touching each other. They're insulated from each other. So this has 4 times the number of turns. Let's just go back to this one, this cheapo magnet. And I was going relatively slow. I mean, I'm generating a lot more current. And what I would be generating is 4 times the current. By the way, I am generating a current because these electrons flow through here. It's like flowing through the light bulb. Okay. So, show the direction of the electron current and the direction of the conventional current in the induced circuit. Next page, or at the top of the next page. I notice now that my diagram up here has this electrical symbol, and yours at the top of page 67 has a different electrical symbol, right? Well, this is called a resistor. It's maybe a heating element in a toaster. That's a light bulb. No difference. Because I've connected this now to some electrical device, the electrons can flow. So what is the direction of... I thought I had them here. I guess I didn't. What is the direction of conventional current? Well, the electrons we decided were forced down, which means electron flow is that way. Throughout the whole circuit, right? Electrons are flowing in this direction. But conventional current is flowing in the opposite direction. So, I think I've set you up for success here with this statement and understanding it. This is called the generator effect. You generate electricity. And I think where I want to end here, because you still have a written response to do for tomorrow to complete, is we're going to end the lesson officially there. But I want to show something to you. I have a generator. This is the same thing we were using over there. Okay? But I'm going to connect it, instead of connecting it to a light bulb, I'm going to connect it to a voltage. I'm not going to turn it. I'm going to connect this, turn it off, to a voltage. And I am at, why not? Let's go to 12 volts. So I'm going to connect this thing. Yeah, 12 volts. And we're going to turn it on. I thought, oh, it didn't work. I got to turn it on, right? It's a motor. What's in here is a motor. There's no difference between a motor and a generator. If I put electricity into a motor, it's a motor. If I decide to turn it around, and connect it to some device that draws a current, and I crank it, it's a generator. And we still haven't gotten to Lenz's law. We're a ways away. But wait. So what is this? Is this a motor or is it a generator? It's both. This is a motor or a generator. So if I connect them together, I have a way to move information from one place to another. Because when I crank, can you just hold that about that height so people can see it? When I crank this, that moves. You see in old Western movies, they got the telegraph, the tick, 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 tick. You know what I'm talking about? Where they tap out a series of taps, and then way over in New York City, they're getting more taps. That's what's happening. Tap, 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 tap. This is what's called electrified codes or information. If we could find a way to break that, then we would have non-electrified. We would have non-wired. Wired is the word I was looking for. So this is exactly, everybody, how a microphone and a speaker works. When I speak into a microphone, there's a little baffle that has wires surrounding a magnet, and the sound moves that baffle. It's a very delicate device. And it moves electrons back and forth through all of this, causing the baffle in the speaker to move, pushing air. And if I'm speaking a certain way, that pattern of air gets reproduced out of the speaker. And that pattern of air eventually hits your ear, and that's what sound is. Go ahead, Ian.
How many revolutions do you get out for putting in one?
Wow, that's a great question. I don't know. Let's start with it on the handle. Can you hold it right there so it doesn't turn? And I'll start with mine on the handle. Okay, you can let go. I don't know. I never would have thought of that question. Half. Now, I don't know. Does that mean, can you put it back to where we started? Does that mean if I turn that a full, this will go 2? I don't know. I don't think so. Can you turn it around once? It goes around a little bit, about a half. So there's some kind of loss of energy there, whether it's to heat or friction or something, where we're not getting 100% efficiency. And by the way, go ahead and crank yours, hold yours up like this, and crank it clockwise. Clockwise, right? Okay. Go clockwise, counterclockwise. Which kind of makes sense. You may not know the exact structure of this. What we're going to do when we start off tomorrow is I'm going to be talking about what's going on in a motor and a generator, and then we can finally connect everything to Lenz's law. Okay? Any other questions? Kind of cool. It's how a speaker works, a microphone, any type of wired transmission of signals in terms of sound is using this principle. Okay. So you have that written response, which is due tomorrow. You don't have any work to do from this lesson. Tomorrow, I'm hoping that I get a car battery that's juiced up enough to show you the wires that are parallel. We may not, though. We'll see. And tomorrow we'll finish this whole episode with Lenz's law. I will pass around, if you want, look, drop it through, but watch the magnet fall. And you might want to work with a partner, that way they can hold it and somebody can catch it at the bottom. Yeah.
That it was like a hybrid, and so you could turn it into, you could shift it into a gear.
Yeah.
That would, it would, instead of braking, what it would do is it would hook up a generator, so that, is that momentum that the force against your hand when you're moving, that brakes, is that Lenz's law?
It's the same idea. It's called regenerative braking. So if you have a Tesla, and a Tesla isn't a hybrid, it's purely electric. But when you brake with a Tesla, I've never driven one, so it'd be hard for me to imagine. There's no brake pedal. You just let off the gas and it brakes. It senses what you want to do. But what happens is when you let off the gas, it connects a series of generators or coils where you get Lenz's law happening, which applies a backward force. That backward force slows down the car. But some of that force as well is used to turn a generator to recharge the batteries. So it's a very efficient thing. And that's the beautiful thing about regenerative braking. There's no friction. There's no heat. Like, my goodness, if you ever drove on the highway and took a wheel off, and then you touched the brake pads, you'd seriously burn yourself. There's a huge, huge amount of heat with friction and brake pads and rotors and all that stuff. And that heat is just lost energy. You can't do anything with it. You can't get it back into some kind of organized, useful thing. But if we can use that energy instead of as heat, we use it to recharge the batteries.
I wonder if reports have come out yet that how much maintenance a Tesla would need because of that. Because there's not very many moving parts.
Okay, no. But what they are starting to discover, and I'm not telling you this because I'm against electric vehicles, far from it. But what they're starting to discover is, yeah, your batteries might last 5 years, whereas a regular car battery lasts maybe 2. But to replace the batteries are very expensive. So even though some of these parts last a lot longer, right now they're very, very expensive. Yeah.
Well, I guess that's just better quality batteries.
Well, and that kind of makes sense, right? If you buy something that's going to last you longer, it makes sense that it's going to be more expensive, right? It's not a shot against Tesla or anything.
Before I start writing down and explaining everything.
So let me ask you a question. The distance that you used here, what did you measure?
I measured with ruler across.
Okay. The distance that you used here, what did you measure?
From this line to the plate.
And the distance that you used here, what did you measure?
I think I used the same one. Should I have used the distance?
You have to use the whole distance because we're trying to find the voltage between the plates. So that's the difference, Colby.